We're going to continue talking about water and solutes and solvents by dealing with acidity. Okay. Now, all solutes have an acidity. The acids is acidic or basic or it's neutral. Okay. And I don't want you to fall into the trap, what I've seen a lot of students do, say that acids burn and bases don't, because that's not true. Acids will burn and bases will burn. And actually base burns are much worse than acid burns. Okay, by far. Okay. But we're just going to talk about acidity, and we're just going to give a general definition of what makes an acid and what makes a base. Okay, so an acid, acidity, let's start here. Acidity. We'll start with acids. An acid is a solute that contributes hydrogen to a solution. Contributes hydrogen to a solution. Now you may be like, what the hell are you talking about? And if that's crossed your mind, I get it. It makes sense. Okay. So when we talked about compounds and the dissolved, those ionic compounds, they like to break apart. Okay. So I'm going to give you an example of HCl, which is hydrochloric acid, hydrogen chloride, hydrochloric acid. When you put HCl in water, this hydrogen, that hydrogen right there, kind of acts like a metal. And what it's going to do is it's going to break off and be H positive. And the reason it does this is because Cl is so hungry for electrons. It's not going to let hydrogen just break off. We're going to keep its electron. No, chloride is greedy for the electrons, and so chloride is going to come off and it's going to have its negative charge when you dissolve this in water. So what HCl, hydrochloric acid, has done when you put it in water, it's donated a hydrogen. It has contributed a hydrogen to that water solution. Now that water now has more hydrogens floating around in it. Okay, where normally it was just H2O, and H2O was doing its thing. When I add hydrochloric acid to it, there's now more hydrogen in that water than there was before. And what that's going to do, what that functions as, is an acid. That's what an acid does. Okay, another way to think of an acid, okay, and this is just how I've done it. It is a proton donor. It is a proton donor. It is a proton donor. Now you may be like, what the hell are you talking about there? And it's really simple. It's really simple. Hydrogen. Let's take a look at hydrogen. Okay, let's draw hydrogen out here. Let's do the periodic table for hydrogen. Hydrogen, it's got an atomic number of 1, AN of 1, and it's got a mass number of 1. Okay, so if we draw out hydrogen, it's got this one single proton plus one proton, and typically it has one electron that's floating around it, right? I mean, that's the structure of hydrogen. Now, what happens is what if I cut this electron off? What if there's no electron there anymore? What do I have left? I just have a proton. And that's what we mean by a proton donor. It puts a proton inside of the solution. It is a proton donor. Okay. Another way to say a proton donor is also an electron acceptor. Because what is that hydrogen going to want to do? It's just a single proton that's just floating around there. It's going to want to take an electron. It will accept an electron. Okay. So what you will see a lot of times in the literature, and things that you write, when they talk about proton donors, a lot of time protons are written as this, H+. They will write protons. And I think it's in your textbook a couple of times where they say H+, and what they mean is that's a proton. That's how a lot of times they write protons. Okay. So don't get lost. Don't get confused. Don't get lost when you see that H plus. That means it's a hydrogen. It's still hydrogen. It is still hydrogen. But if you want to get down to the nitty gritty of what is hydrogen, it is just a proton. I mean, that's all hydrogen is. Okay. Now you'll be like, well, can you have an isotope? Can you have an isotope? Yes, of course you can. If I have a proton and a neutron inside of that nucleus, is it still a proton donor? Yes. It still is. Neutron doesn't do anything. It's just sitting there being neutral. Okay. It is the proton that does the work of the acid. Okay. Now, acids can be either weak or strong. Okay. So you can have a weak acid or you can have a strong acid. Okay. So now the definition of a weak acid versus a strong acid. So a weak acid, sorry, no, let's start with strongs. So a strong acid will totally dissociate in water. Okay, I'm just going to say separate in water. Okay, totally separate in water. Okay, whereas a weak acid does not. Does not totally separate in water. Okay, so we're going to, in lab, we'll talk about, I'll give you examples of weak and strong acids, but that's what it is. So the biggest one that we're going to work with, we're going to pretty much be working with strong acids themselves. And hydrochloric acid, HCl, is a strong acid. Okay, so now there are some people who say that, oh, weak acids, what they do is they don't drop the pH as much, and I was like, that's just absolute nonsense. That's just nonsense. Okay, weak acids do not totally dissociate. Strong acids totally dissociate. Okay, so that's what I want you to remember about weak versus strong acids. Okay, so acids. Here's what you got to remember about acids. Hydrogen. It contributes hydrogen to solution. It puts more hydrogen in a solution than normal. Okay, so what this means is it's donating a proton. It's putting a proton in solution, and it's also an electron acceptor. I really don't care if you remember the Lewis definition being electron acceptor. It doesn't bug me that you don't. I just remember when an acid adds hydrogen to a solution. So what's going to happen here? So let me give you an example. So if I have hydrochloric acid, so we have HCl. So what this is going to do, and if I put this in water, this is how it's going to look when I put it in water. Okay, that's how it's going to look. Okay, I'm going to put all of that extra H plus inside of the water, and there's going to have more hydrogen inside of the water. That's all an acid is. That's all an acid does. Okay, so don't get too caught up on it. Don't flip out. All right. So now a base. There are a couple of ways we can define a base. Okay. But I'm going to do it like this. It is a solute that removes hydrogen from a solution. Okay. Now, if you understand what acids does, a base is pretty much the exact opposite. Of what an acid does. Okay. So, an example of this would be like sodium hydroxide. Sodium hydroxide, NaOH. This is called sodium hydroxide. Okay. Sodium hydroxide. Now, if you put sodium hydroxide, okay, this is an ionic bond because we got that metal, and we got the non-metal. So we got the metal sodium, we got the non-metal hydroxide part. When this gets put in water, we're going to have the sodium that's going to float around, and then we're going to have the OH, which is going to float around. Okay, all right. So now you're like, well, why doesn't the hydrogen skip off? You know, and in some cases it does, but in most cases it really doesn't, because the oxygen's affinity for the electron isn't as strong as like chlorides is. So the hydrogen tends to stay attached to the oxygen. However, the oxygen is still pretty greedy, so it's going to take all of those. It's going to take all of those hydrogen. It's going to take all of those electrons, and we're going to have a negative charge still on the oxygen. So now, if you look at this, and you take this OH. This is called the hydroxide ion. Okay. Now, if I have a bunch of hydrogen just floating around here like this, they're going to react together, and they're going to make water. Okay, and when I make water, if I put hydroxide in a very acidic solution, what it's going to do is I'm going to put more water in. So I am removing the hydrogen from the solution. So I'm going to make it more basic. I'm taking the hydrogen away. Okay, it removes from the solution. Now, a lot of people, when they think it removes it from the solution, I'm just taking it out of the solution. It's just going bye-bye. No, it's not. It's not really doing that. What I'm doing is basically I'm turning it into some kind of non-reactive form. So the hydrogen is not going to be reactive when it's in water, attached to water. Okay, that's what we mean. Okay, so another thing that a base is, it is a proton acceptor. It is a proton acceptor. It is a proton acceptor or an electron donor. It will donate electrons. And again, the electron donor is a Lewis definition. I really don't, you don't have to, that's not as important for me to know this, but I just wanted this for completeness. And if you wonder like where are the electrons coming from, there's the electrons. Okay, the electrons are on that negative side, and it's got more electrons. It can give some electrons to that hydrogen, and the hydrogen is the acceptor. The hydrogen will take them, and you'll make water in the taking. So that's how that works. Okay, just like an acid, we can have weak or strong, and the definitions of a weak base and the definition of a strong base are the exact same as the definitions for an acid. So a strong base totally separates. In water. And a weak incompletely separates in water. Okay. That's all you got to know about weak versus strong. And again, when we do the acid buffer stuff in lab, we're just going to be pretty much working with strong bases. Okay. So that's the definition of an acid. That is the definition of a base. Now you're like, well, how do we use them? Why do we care? Why do we care? How do we measure it? And so what we're going to do is we're going to talk about the pH scale. The pH scale. Now what the pH scale is, it is the hydrogen potential. The pH scale, it is the hydrogen potential. Of a solution. Okay. It's a real way to measure the concentration of hydrogen. It measures the concentration of hydrogen, H+. And the way I write it, H+, is you put it in brackets. When you put something in brackets, that means concentration of what's ever in the brackets. So inside the brackets, that means the hydrogen concentration. Okay, so now how do you calculate it? Okay, so now I'm not going to make you actually do math. I'm gonna, when I do this, I'm going to make sure that you understand the concepts. Okay, and what it is the pH equals the negative log, okay, of the hydrogen. Okay, if you want to actually be technical, it's the H3O. If you want to get really, really technical, but this is the one I want you to remember. Okay, that's the one I want you to remember. Okay. Now, the log means we're going to be going in multiples of 10. Okay, we're in the log. Okay, so And it's an inverse log, so we're actually going to get a nice whole number. So don't worry about that. So what this means is if I have a solution that is neutral, 7 is neutral, okay? It has 10 times more hydrogen than, oops, a pH of 8. Okay, and as a descending scale. So if you look at it, 7 is neutral. When you go this way, and the numbers get smaller, 6, 5, and you go this way, and the numbers get bigger. Okay, this is more acidic. This is more basic. So the larger your pH, the higher the number of the pH, means it's more basic. The lower the pH means that it is more acidic. More acidic. Okay? Right? So if I go from 7 to 6, that means there's 10 times the amount of hydrogen in that. So if I'm going to 7 to 6, I have to add 10 times as much hydrogen. If I go from 6 to 5, I have to add 10 times as much hydrogen. If I go from 8 to 7, I have to add 10 times as much hydrogen. So now if I wanted to go from pH of 7 to 6, I'd have to add 10 times 10, or 100 times as much hydrogen. If I wanted to go 8 to 5, I'd have to add 10 times 10 times 10, so 1,000 hydrogens. So we might have to multiply it up in order to get what we want. So I'm going to draw out a pH scale. pH scale. So here, 7 is a pH, is a normal pH scale. So then you have 8, 9, 10, 11, 12, 13, and 14. Okay. Then you have 6, 5, 4, 3, 2, 1. And theoretically, you can, no, not theoretically, you can get to pH of 0. Okay. So at 7 right here, we are at pure water. Pure water. Now you may be like, well, wait a second, dude. Water is H2O. But in an earlier lecture on water, water doesn't exist just as pure H2O. It actually exists as this at any given time. And it goes back and forth. Actually, I don't want to do the double arrow like that. It goes back and forth equally between these two states. So this means you have some free hydrogen floating around. Okay, so there is some hydrogen in pure water because it's just the way water is. Water exists between the H2O form and exists between the H plus and the OH form. Or another way that people will write it is H3, oops. They'll write it as H3O plus OH. Okay, but that's not stoichiometrically nice, so we're just going to ignore that. Okay. So that's the way water exists. Okay, so now if you get to the most basic out here, this would be 1 molar sodium hydroxide, NaOH. Okay. Okay. And then if you get over here to the 0, this is 1 molar HCl. Okay, so that's moles per liter. Okay, so molar means moles per liter. So this 6.0 times 22 times 10, 6.022 times 10 to the 23rd atoms, HCl in 1 liter of water. Okay, so that's the Avogadro number here. And on the other side of the basic side is going to be the 6.022 times 10 to the 23rd of sodium hydroxide. So that's about the most basic you can get, and it's like the most acid you can get at a 0. And at the bottom we have pure water. Okay, so now blood. Okay, one of the objectives for the course is blood. So blood is actually a little bit basic. And it's got a very narrow range. That's blood. It's about 7.35 to 7.45. That is blood. That is the pH of your blood. That is normal blood pH. Very, 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 very narrow. Now, don't let somebody, I know other people at the college will tell you that this is the range, and anything below that or above that is abnormal. I've seen people below 7.35 and they're perfectly fine. And I've seen people above 7.45 and they're perfectly fine. Okay. If they're below 7.35 or actually below 7.3, that's called acidosis. Okay, it's called acidosis. Actually, let me put it in a new spot. Below 7.3, I'm sorry, 7.3 is acidosis. And above 7.5 is alkalosis. This means your blood, acidosis, this means your blood is more acidic than it should be. Alkalosis means that it is more basic than it should be. And if it's normal, if it's not from a disease state, if a disease isn't causing this, it is called physiologic. Okay. You know, if it's just the way you are, it's physiologic acidosis and it's physiologic alkalosis. Okay. Now there are a bunch of diseases that will cause you to be acidotic and you'll be alkalotic. Okay. So you can be acidotic if you vomit a lot. If you do a lot of vomiting, you can be, or you have a lot of diarrhea, you can become acidotic, and that's not physiologic. That there's the disease or something is causing to do that. You can become alkalotic if you drink like a lot of milk, or or you take a lot of Tums. That can cause you to be alkalotic, and that's not physiologic. That's something you've done to yourself in order to do that. But normally, the little bits are not going to do that. Now, if you get the lowest ever recorded, I think, of acidosis it's like 6.53. That's actually made a recovery. I've never seen anybody go below 6.8 and make it back. Okay, so this means that there's a very narrow range of acid and base. And when I was in medical school, there was this one guy lectured me, anything below 7.2 is incompatible with life, and I was like, that's nonsense, because I've seen it happen. We'll talk about that when we talk about blood and we talk about the kidneys. About how the kidneys how the kidneys and how the lungs will try to keep the acid and the blood normalized. But just right now, no, 7.35, 7.45 is our blood. Okay. One of the interesting things I find about this acid base stuff is if you look at this, if you look at around the 9 and 10 area, 9 and 10 here, this is bleach. That's bleach. Okay. 11 and 12 is ammonia. So these are the cleaning solutions. So the cleaning solutions tend to be more basic. Okay. So here, slightly below here, like 6.5. This is saliva. Saliva around the 6.5-ish area. Okay. Again, you don't have to remember this stuff. Beer is about 3 on the pH scale, so beer is pretty acidic. Okay, about 4. These are the tomatoes. Tomatoes are about 4. Okay, stomach acid is here. Stomach acid is about right there. Okay, about 1. Okay, stomach acid can melt lead. So it's very, very acidic. Okay, so beer 3, grapes, tomatoes about 4, saliva is about 6.5, almost basic. Pure water is 7. Okay, is 7, and then we get blood 7.35. This is the important one, 7.35, 7.45. That's the important one to remember. put a little star next to it. Okay, and then once we get there, we get to the household cleaning stuff. Now, I'm not going to make you, and anybody who does this is just a dick, okay? I'm not going to give you like a pH of 11 and say, what is this? You know, what household item is that? No, the only pHs I want you to know is I want you to know anything below 7 is acidic, anything above 7 is basic. And the only numbers I am really going to want you to remember is 7.35 to 7.45, because that's blood. Okay, anything else, Okay, when we go to the digestive system and we talk about stomach acid, then maybe I'll like, what is the pH of stomach acid? But right now, for the first test that we're going to do on basic sciences, you do not have to know that. Okay, it's more important for you to remember how much acid I have to add in order to change the pH. Okay, that's far more important. So if I need to go from a pH of 7 to a pH of 6, I have to add 10 times as much acid. So if I add 1,000 hydrogens and the pH of a solution becomes 7. Okay, that's just giving you numbers. How much do I have to add to get it to become a pH of 6? And basically all you got to remember is, I got to multiply that by 10. So 1,000 times 10 is 10,000. So I have to add 10,000 hydrogens in order to make it become a pH of 6. If I need to go from a pH of 6 to pH of 5, I have to multiply that by 10. 10,000 10, I have 100,000. Okay, that's what I want you to remember. That's the principle. That's the principle, by tens. pH scale is by tens. Okay, so I think that's all we really need to know about acids and bases. Let me think. Let's see if there's anything. Okay. Oh, buffers. Okay. So the last thing is buffers. Okay. So what a buffer is it's a compound. Buffer. It resists. It is a solute that resists pH change. Solute that resists the pH change itself. Okay, so let's just say that I have, and it's typically, before that, it's typically a weak salt or a weak acid. A weak acid. It's not salt combination combo. So basically what it is if you have, and I'm not going to go into the definition of how to calculate weak acids and everything like that. So typically if you have this HA, we're going to call this a weak acid. Okay. Actually, I don't want to do it like that. Okay, so what this means here is that typically this acid right here exists in that state because we're pretty much being pushed onto that one, into this one. So this means this acid is not very active. It's not very active. Okay, so one of the rules of reactions is if I put a solution that has a lot of hydrogen, let's say I add a lot of hydrogen to this side of the equation. What that's going to do is it's going to force the reaction to go in this direction. It's going to force it in that direction. And what that's going to do is it's going to take up excess hydrogen. It's going to take up excess hydrogen itself. So what a buffer does is it actually prevents pH changes. Not prevents. I don't want to use that word. That's a bad word. It reduces pH changes. Okay, so like if I have something as at 7, actually it's never going to be 7, that's pure water. Let's just say I have a solution that's got a pH of 8. I have a pH of 8. Okay, with a buffer. Okay, with a buffer. So with buffer. And then I have a pH of 8, no buffer. Okay, and if I add acid, W is with. with buffer. Now, let's say I add an acid. So I put an acid here. And the pH goes down to 7.6. 7.6. And then I add the same acid to the no buffer, and it goes down to 5. What has happened is the buffer has prevented a pH change. The pH did change. The pH did change. Don't let anybody tell you that a buffer won't, with a buffer you can't change the pH. You can. You can totally change the pH, but it's not as drastic. Not as drastic. If I add an acid to a non-buffered system, I'm going to get radical changes in pH. But if I add the acid to a buffered system, I'm going to get much less radical changes. And that's the only thing I want you to remember about buffers. Okay, you don't even have to remember the acid salt combo. You can just forget I said that. Actually, just forget I wrote any of that crap down. I just need you to know what a buffer is. Okay. Now, the last thing we would do is I want to talk about salts. Salts. Okay. So now your textbook says the result of an acid-base reaction. That's what your textbook says about salts. So if I have hydrogen chloride, HCl, plus sodium hydroxide, NaOH, okay, and I react them together, okay, what I'm going to get is I'm going to get an exchange reaction. Okay, we've seen this before. Okay, the hydrogen is going to react with the OH, and the chloride is going to react with the sodium. Because what's going to happen in water? What's going to happen in water is this H is going to come here, and this is basically what it's going to look like once you're in the water. Okay. So I've got the dissociation of the hydrochloric acid, and I've got this dissociation of the sodium chloride. Okay. So now you can use just basic charge to figure out what's actually going to happen. The hydrogens and the sodiums aren't going to be attracted to each other whatsoever. Okay. They're not going to be attracted to each other whatsoever. They're going to repulse each other. Okay. But the hydrogen is going to be attracted to the hydroxide. And what that's going to do is it's going to give us H2O. Okay. Now, a salt, by definition, has to be an ionic bond. Okay. It's got to be an ionic bond. Okay. So H2O is covalent bond. That's not a salt. Okay. Then the other thing that we have is we have the chloride. It's going to be attracted to the other positively charged ion itself, and we're going to get sodium chloride. This here, ionic bond. It is the reaction of an acid-base reaction, because here's our acid, here's our base. It's a result of an acid-base reaction, and it is a salt. Okay. When I was young and going through and learning chemistry for the first time, when I was an undergraduate, I had this guy tell me a salt is an ionically bonded metal to a nonmetal. That's what a salt is. An ionically bonded metal to a nonmetal. So if you look at this, metal. If you look at this, nonmetal. Okay, ionically bound metal to a nonmetal. So that's the easiest way to do it. So the first two columns that we're going to look at when we're dealing with this, we're going to look at the alkaline earth metals, and we're going to look at the alkali metals. So sodium, chloride, magnesium, and calcium pretty much are the only ones we're going to be dealing with. So if you see sodium, you see potassium, you see magnesium, you see calcium, okay, as the cation, and you see it bound to something else, it's got to be an ionic bond, and it's pretty much a salt. It's pretty much a salt. Okay, so I know that's probably not going to be a universal definition, but it's one that's actually served me pretty well throughout most of my career. So a metal ionically bound to a nonmetal is a salt. Okay, or you can use the textbook definition. Textbook definition works just as well. It is the result of an acid-base reaction. See, but in my brain, it's like you don't have to have an acid-base reaction to make a salt. And I think the book's definition is very limiting to us. But that is it. that is it. We have covered everything else. So we've talked about acids, we've talked about bases, we've talked about the types of solutions. We've talked about the pH scale. I talked about the range of pH. I've talked about physiologic acidosis, physiologic alkalosis, and buffers and salts. And I think we've covered everything. And again, I'm sorry, it was much longer than I wanted it to be, but I will do my best to keep them much shorter from now on.